Now that we've taken a look at some orbitals and starting to get interested about that, let's figure out how in all this infinite dimensional space we can pull out the things that are important. Pull out the things that actually are defined by the energy. Now this gets into the Schrodinger equation, so let's just jump right in. Here are some energy operators. And the energy operators are the Hamiltonian, which is what we love to talk about, plus a couple others we don't normally mention specifically, and one of them is the kinetic energy term. Now that T comes from a French word, we won't worry about that, and V for potential energy, which probably that doesn't bother you as much. But each one of these are an operator. The kinetic energy operator is, now this should look familiar to you. If you remember, p squared over 2m was for classical kinetic energy. Now we have minus h bar squared over 2m, and this funny looking weird triangle, which is the Laplacian, which I spent a lot of time developing in a previous series on the Schrodinger equation. Then finally potential energy, and this one should look really important. Here's a couple of electron charges, one the nucleus, one the electron, so that gets squared over this famous part here, 4 pi e to the 0 r. And these are this is the Coulomb law. Now what about these? What about electron-electron terms? Well, what if the electrons are near each other and you've got electron repulsion? Well, that's a really important thing. So we have to include those. Now, let's try and figure out if we can make this in action and finally solve something with this Hamiltonian that'll spit out the correct energy-specific orbitals that are involved. Oh boy, oh boy, oh boy. This is the state function of R, which is the spatial thing in real space, but for each one of these, this cranks out a complex amplitude that can be used to predict probabilities. And the probabilities help us figure out where in the heck the electron is in this space. And this space, just as a reminder, is represented by this god-awful looking thing. It's not so god-awful except for the L squared. You're thinking, L squared, what's L and what's the square? Well, this has to do with that property of square integrable functions, which allows us to crank out the probability. Now in this, there's some questions here. Let's see if the questions even make sense. We might have to fight with the questions. How does a state change? What do you mean change? Well, how does it change over time? Is it just static? No, you can be sure it's not static. So what happens to it over time? And this other thing is, what states persist except for a phase change? I think these two are related. Because if the states persist except for a phase change, then the state change probably has something to do with the phase change as far as time is concerned. That's probably a bunch of gobbledygook. Here was our Hamiltonian. If we can use this Hamiltonian to predict what those states are, then it's still going to be a member of this crazy state, this crazy Hilbert space. Let's look at some things and see if they make sense. This is from the time-dependent Schrodinger equation. This IH bar is directly from the Schrodinger equation, and here's the partial with respect to time. That shows that why it's the time-dependent Schrodinger equation. Okay, if that's true, well then what about this effect? If we take the Hamiltonian operator and operate on this state, then we should be able to come back with the energies. This is the Schrodinger equation for sure. Let's look at this. This adds a little bit. You got a psi of a function of the r value and the time, and we get this neat looking little thing. And what's neat about it is, here's the energy, and here's the I value over time. So we've got an oscillating energy term. Now I think that makes sense. Let's get spin involved, because remember all that time we spent on spin? Now that's important because guess what? It's out there. You can't ignore the spin on an electron just because you're focusing on the orbital. So let's look at some of this stuff. Let's look at a total state of R. Here we've got this big capital psi. This equals, or this is represented by spin up and spin down. Big surprise. But if we add spin up and spin down, we are going to have to add a couple more dimensions. And this is an element of, this is that weird thing that we've been fighting with, the square integrable functions that operate on real space. And this one should be familiar to you. No big sweat if you watch the spin part of this series, or that's a separate series. But here's the other. So I'm going to bring in something else. Spin, we said, is an intrinsic angular momentum. Intrinsic, nothing spinning. But orbital angular momentum, something is spinning. So when we figure out what the L vector is, now that's not the same L as what was up here, so that can be confusing. No, this is L for angular momentum. This is not for angular momentum. So we take the position in space and cross product with the, what do you think P stands for? P, not P orbital, it stands for momentum. And so that momentum will tell us something about the shape of what's going on. If there was no rotation, and no angular momentum, and there was nothing to this cross product, then we wouldn't have any angular momentum. But angular momentum can be represented as, and this looks similar to the Schrodinger equation, negative I h bar r vector cross product with the Laplacian. Yes, I said it, the Laplacian, which is kind of like a second differential type thing in vector space. Now let's go back to spin operator. This should be review. If not, you have to go back and look at the playlist series and maybe hunt and peck for the particular item that talked about the Pauli matrices. And this big S is the spin operator, and we showed that the measured value for the spin operator is h bar over 2 times the Pauli matrices vector. I put bar over there to show that it's a vector. And that has x, y, and z components. You should know these matrices by heart. If not, go back to the spin stuff. I keep saying that. Okay, now let's talk about a total angular momentum, J, which equals the rotating angular momentum of the electron and the intrinsic spin operator. And we call this total angular momentum J, because we're running out of letters. We have to use J here. I'm also going to show that the dot product between the the angular momentum, orbital angular momentum, and the spin angular momentum, the dot product is called the Hamiltonian spin operator. So this is when these two things are coupled together. And this is where things get really interesting, and it helps us with chemistry down the line. This page is packed full of neat stuff. It really shows how all our work in the past is starting to come together. Look at the quantum number L. Quantum number L can be 0, 1, 2, 3, onward up to n minus 1. What's the n? Well, the n is the principal quantum number. I'm switching to this page because the last one didn't really have an explanation of n, I mean. N is 1 here, and I'll just go down the pike here, and I think you'll get the idea. The n, the principal quantum number, changes here, changes here, changes here, and it just keeps going till down here. And isn't it strange? I've got a 1, 2, 3, 4, 5, 6, 7. These are the periods of the periodic table. In all these cases, the L value can get as high as 6 here because it's n minus 1. The M value will be governed by what the L value is. L is orbital spinning angular momentum. M is intrinsic spin momentum. L helps determine orbital shape. Isn't that cool? If L is 0, it's the S-type shape, and each one of these has a different shape to it. And the L value goes up. Now, when the L value goes up, that allows a higher range for the M value. Just giving you a little taste for it, before we had the p orbital that we kind of delved into a little bit and got those shapes out of there, which were quite different than the spherical shape for this S value, where L was 0. So when L is 1, what happens is that we can have, what kind of M values can we have? Well, if it's 1, we can have a minus 1, a 0, and a 1. Count them, 3. Count the p orbitals, 3 p orbitals. So this is all kind of falling into place. The orbital angular momentum magnitude can be determined from the L value. So let's take the L value where it's 0. If it's 0, then what does that give us? That gives us 0. This means that L is 0. This means that for the S orbital, there's no angular momentum. Well, how can that be? Well, the S is a stationary cloud. The S is just a fixed probability at a certain radius. So it's really not rotating at all. And remember, the electron is not a point rotating around there, otherwise it would have orbital angular momentum. Now, when we go to L equals 1, then what's the magnitude? Is h bar times the square root of 1 times 1 plus 1 is square root of 2. So h bar square root of 2 is the orbital angular momentum magnitude. This kind of hints at why the P has these lobes in there, because it is not symmetric on the different axes. So this does give it angular momentum. And here are the px, py, and pz shapes represented by the M. Notice the little l down here for angular momentum of -1, 0, and +1.